You're right, sir. How are you, man? Yeah, sure. Yeah. Yeah, you can do that anytime. Okay, that's fine. All right, guys. Hello. Hello. You guys had all good weekend or what? Huh? Yeah. All right, I like to talk about, first of all, what remains in this course, right? Now, this week is week 9, as you all know, right? So we are doing sheet 9 in the example classes this week. After this week, we have a break until, I think you guys really deserve a break. You've been working very hard for 9 weeks, guys. I think you've been having many midterms. I guess you must be really tired by now, right? So you guys deserve a break. And when you come back after the Easter, you have week 10. And we will have, on week 10, we will do, for the example classes, we will do sheet 8, yeah? Yeah, and also on the 25th, 25th of April, it will be a revision class. 25th of April will be a revision for the test. So you can bring all the questions you have for the in-class test on the 25th. I mean, that doesn't mean that you can't ask me any questions before that. You are most welcome to you're most welcome to send me emails anytime, even at night time, even after midnight, if you like. You can send me emails asking any questions you have on this course, right? Okay, so feel free to send me any time, any day, Monday to Sunday, for emails any time of the day. Okay, then on the 26th of April, we have the test. Yeah, we have the test. The test will be, as I said, it will be 1 hour long. Did you all get my email about the test, about the details about the test? Yes or no? Yeah? You got all the details about the test, and the test will be marked by myself on the same day, so you will get to know your mark and the feedback and how you did on the 2 questions within 24 hours of the test, right? That is, before you should know all the details of your performance before the 27th of April, right? Then also the syllabus. Also, the syllabus for this course will be completed in week 10 of the course, right? All right, guys. And in week 11 and week 12, it will be revision for the exam. It will be revision for the exam, right? So week 11 and week 12 will be revision for the exams, guys. So the syllabus for this course will be completed in week 10, guys. Okay? So this is the plan for the rest of the semester, guys. You have any questions? Yes or no? Any questions on the midterm? Just please have a look at the emails I sent to you about the material that will be covered. Shh. Please have a look at the email I sent to you about the materials that will be covered by the test, by the in-class test. I think it's only the first 4 weeks of material that will be in the in-class test, if I remember correctly. So you don't need to know everything we have done up to now to do the in-class test, right? I think it's only the first 4 or 5 weeks, if I remember correctly. Okay. Now, before I go back to test of hypothesis, today I'm going to just carry on doing test of hypothesis. There was last week there was some confusion with some of the material I covered. It's not confusion, it's basically different approach, I guess. You know, you guys remember, when I talked about testing for proportions. Yeah, this is good. You guys remember this from last week, guys? This is testing. I should put this here. Right, we talked about last week one sample test for proportion. And I gave you, the assumption was that All right? The assumption was that you have a data set that are IID Bernoulli variables, right? And we wanted to test, you may remember this, guys. We wanted to test three different hypotheses. The first one was this. The second one was this, and the third one right. So let me one more time. Let me put the lines. Right. Now for these three hypotheses, right, I gave you the rejection rules as this one, and this one. But there are also other rules, because some of you guys talked to me after the lecture last week, and you told me that there's some other lecturers who taught similar stuff, gave you other rules. I mean, as you know, in statistics, there's no one rule for doing things. There are different rules for doing the same thing, right? So even so there are some other rules apart from these ones. You can also reject H0 if you can reject H0 if this is the case, right? Instead of this, guys, instead of this, you can use also this rule. This rule is also okay to use, right? Okay. And instead of this one, you can use this one too, right? And finally, instead of this one, you can also use this one. So that's all I wanted to say, because some of you guys asked me last week after the lecture about, because I know people who taught, like for example the intro to statistics you took last year, maybe use these rules instead of these ones. Maybe the lecturer who taught it, maybe use these ones. So I just wanted to say that these two rules are, although they are different, both of them are acceptable, right? Okay. All right, guys. So I just wanted to avoid the confusion you had last week, right? Right. Now let me go back to. So this is just a comment on the stuff I did last week. Right, let me now go back to where we were last week with the stuff we did. All right, this is the stuff, if I remember correctly, guys. This is what we did last week, you may remember. This is inference for equality of means, when we assume that the variances of sigma x squared and sigma y squared are known. And these are the three different hypotheses that we looked at, 13, 14, and 15, right? And these are the corresponding rejection rules, right? And now what I'm going to do, let me put this over here. Now what I'm going to do here is, well, I was in the process of deriving the power function for test number 13, which is this one. This is the power function for test 13. I was in the process of deriving it, and I got to this stage where I ran out of time. Now, I asked you guys to complete this. Did you have time or no? Did you have time to complete this? Yes? No? All right, anyway, if you did not have the time, let me complete this, because This is where I stopped last week, guys, right? Now, because x bar minus y bar has this normal distribution, we need to do some kind of standardization here, guys, right? The standardization I'm going to apply is the following. So I'm going to, hopefully you can see what I'm writing. Right, the standardization I'm going to apply, I'm going to before I do any standardization, I'm going to multiply right. You see what I've done here, guys. You look back from this step to this step. What I have done is to multiply the two sides of the inequality by this term, and the same thing here, right? Okay. Now I'm going to do the standardization. Because x bar minus y bar has this distribution, right? To do the standardization, remember, you need to subtract the mean and divide by the standard deviation, right? So right, you see what I've done? I've subtracted the mean and dividing by the square root of the variance. So I do that both sides. I know it's a laborious job, but you have to do this though. I know it's all right. I've done that on both sides, and I need to keep the conditioning that mu x comma mu y. All right. This is only for the first term. Now we've got to do the same thing for the second term, because remember there are two probabilities. There are two probability terms, this one and this one. All right? Okay. Now, let me ask you guys, now what can you say about this? And I've done this enough times, guys. And this. These two guys, because of the fact that x bar minus y bar has this distribution, these two guys must have the standard normal distribution, right? You follow? Both these should have the standard normal. So So what we have is that the probability that NO1 is, greater than or equal to, right? So this is what you get. And the conditioning is no longer needed because the conditioning have been used. The conditionings have been used to argue that these two have the standard normal distribution. All right, the final step is you can, if you like, you can write this as 1 minus phi yeah, and this one you can write as phi or phi at all right. So what I have written here is the power function of mu x and mu y. Yeah, I know it looks like a long calculation, but long, boring calculations, but this is, unfortunately, this is sometimes you have to put up with this. Yeah. Okay. Any questions on this, guys? Are you okay with this or no? Yeah. Yes. Some of you look. Yeah. All right. All right. Let me put this over here. This is. Let me put this over here. So we have proved. Now the rest of the things I'm not. Let me. So that's. This what I have derived here, guys, is only for one of the tests. Remember, there are 3 different tests for every parameter. There are 3 different tests, right? And what I have derived here is only for test 13. So homework for you guys. Derive So this should be 14, I think, 14, 15. Right, I would like you to, whenever you have time, please try to derive the power function for test 14 and test 15. Now what I have derived here this is the power function for test 13. And 14 and 15 are, this is 14, this is 15, okay? All right, guys, okay. Next one. Next one I'm going to consider is testing. I'm going to consider testing equality of means when Right, I'm gonna, so far we considered testing equality of means when the variances are known. But in practical situations, there's hardly any situation where the variances are known, all right? So the tests that we have considered so far are not not realistic, right? So now what I'm going to do is, all right, suppose, let me get my glasses. All right, so once again, we got two random samples. Both of them are from normal distribution. The first one is from a normal with mean mu x variance sigma squared. The second one is from mean mu y variance sigma squared. And sigma squared is assumed to be unknown. And we are assuming once again that the two samples are independent of each other, right? And we want to test one more time the three sets of hypotheses, mu x, the two means are equal versus the alternative that they are not equal. And sorry. All right, these are the three sets of hypotheses as before. Oh, sorry, man. Okay. Now, for the first test, right? For the first test, you reject the null hypothesis if this is greater than the percentile of the t distribution with degree of freedom m. I don't know whether you can read this, guys. It says m plus n minus 2, comma, alpha by 2. Alpha divided by 2, guys. I'm sorry if this is not clear. And for the second test, sorry, it should be minus 2, yeah, that's what I said, yeah. Minus 2 comma alpha. And for the third test, all right, these are the three rejection rules for the three different hypotheses, right? Now here, SP squared is known as a sample, is a pooled SP squared is known as the pooled sample variance and is defined as follows. This is known as the pooled sample variance. Okay? Whereas SS squared is the sample, SS squared is the sample variance for the first sample, and SY squared is the sample variance for the second sample. So this is simply this is the sample variance for the first sample, and SY squared is the sample variance for the second sample. Okay? Now, okay guys, now let me put this over here, guys. Now, I'm not, well, let me label this before I forget. So this is, I'm going to call this 16, I'm going to call this 17, I'm going to call this 18, right? Now, I'm not going to show you, because I think I have a few things to cover, so I'm not going to show you how to derive I mean, given what you have learned in this course, you should be able to derive the power functions for 16, 17, and 18, right? Because of the time constraints, I don't have, but I can give you a hint. If you like, I can give you a hint. The hint is as follows. You know, had you seen this kind of things before? Sorry, it should be sigma squared, not sigma x squared. Sigma squared, yeah. This times this divided by this will have what distribution? Chi-squared, yeah. Chi-squared with m minus 1. Come on, guys. I just... Don't you remember equation 72 in the lecture notes, right? And similarly, n minus 1 sy squared divided by sigma squared will also have a chi-square distribution by, once again, equation 72. Now, if this is where the knowledge that you learn comes in, guys. Now, if if you add these two, what distribution will that be and why? I mean, we learned this several weeks ago. If you add two chi-squared variables, what distribution will that have? Exactly, yeah. Don't you remember this, guys? Then I'm sure you do remember, right? This is a property that what I asked you to prove. This is by, if you look at page 17 of the lecture notes, you will see that you should have two independent chi-squared variables, then their sum is also a chi-squared variable. That's a property I asked you to prove some time ago. Yeah. All right. So what this says is that it says that this is distributed as sigma squared times this. So in other words, SP squared is distributed as sigma squared and when you derive the power function, guys, just listen to me, guys. When you derive the power function, you will need to use this result. You will need to SP squared is the pooled sample variance I just mentioned a couple of seconds ago, right? So you will need to use this result to derive the power functions for 16, 17, and 18, right? If you have difficulties, come and see me in office or during the example classes, okay? Is that? I hope this hint is enough for you guys to derive the power functions, right? Right, now next, the next thing I'm going to do, sorry. All right, the next thing I'm going to do, guys, is to show you what happens when you have two independent random samples and their variances are unknown and they are not equal, right? So what we do is the following. We suppose that you have a sample x1 to xm, IID, normal with these parameters. And then you have another sample y1 to yn, IID, normal with this, right? And we assume right, we also assume that the variances are unknown and not equal, right? So in this case, this is the most general case, guys, right? In this case, once again, you can test for the three hypotheses. This is the first one. The second one is all right. So these are the three hypotheses, and the rejection rules as follows: reject this is new, okay, not to be confused with A. And the second one is and the third one all right. So these are the three different tests for the three hypotheses, and in these tests, nu is given by the following expression, guys. It's given by, just be patient with me, guys. It's a nasty expression. Right, and I must say that one thing is that these tests are not, let me put this in red. These tests are not most they are not most powerful. I mean, the reason being that because they are based on an approximation. I will not tell what an approximation is, but these three tests, this one, and this one, these three tests are based on an approximation, and therefore they are not most powerful. Whereas the test, sorry, I forgot to say, these three tests, I should have said, I mean, let me put this here. These tests are most powerful. You know the word most powerful. the two words most powerful means that they were derived using the Neiman-Pearson lemma, right? Okay, but these three, which I can call them, say, 19, 20, 21, these three tests are not most powerful because they are based on an approximation. They are not based on an exact result, right? At this stage, I'd like to mention one thing. This year, there was a paper published this year, 2017, that gives you exact tests. I mean, these, as I said, these tests are approximate because they are based on an approximation, right? The exact tests have been derived for this case where the variances are unknown and the variances are not equal, right? It's actually a paper by myself and a student of mine. So I will give you the reference later. You know, it's a PhD student of mine named Roy Lee. We wrote this paper, which was just published this year, where we derived for this case. I mean, this is one of the most open, one of the difficult problems in statistics that has remained unsolved for many years, because it's not easy to solve this problem. You can get an approximation, but getting an exact result is not easy, right? But a student of mine and myself, we solved that problem, and if you look at, I will send you a copy of that paper later on this evening or tomorrow. You should really want to look at it, okay? Okay, guys? Now, I don't expect you to derive the power function for this, because it will be really complicated, guys. All right, so don't worry about this one. I'm not going to ask you to derive the power function for 19, 20, or 21, but you should be able to derive, guys, you're listening, you should be able to derive the power functions for the three earlier ones, which were these ones. I mean, you should be able to derive the power functions for 16, 17, and 18, right? Okay. Now the next thing I'm going to talk about, I'm going to skip the paired data. Do I have time? I think I run out of time now. Maybe I will do that. I'll do that tomorrow, guys. Tomorrow, when you guys come, I will talk about testing equality of proportions and testing equality of variances. Right? That's for tomorrow. Okay. All right, sir.